So just like optical astronomy, radio observations can be made from the ground. Pioneering radio astronomers had the first opportunity to explore a parallel universe containing unexpected new objects such as radio galaxies, quasars and pulsars, plus very cold sources such as interstellar molecular clouds and the cosmic microwave background radiation from the Big Bang itself. Telescopes observing from above the atmosphere has since opened up the entire electromagnetic spectrum to astronomers, but radio telescopes retain a unique observational advantage. Sensitive, multi-element aperture-synthesis interferometers can image complex structures with angular resolution and absolute astrometric accuracies approximating micro-arcseconds. Also, their coherent signals can be shifted to lower frequencies and digitized, permitting the construction of radio spectrometers with extremely high spectral resolution and frequency accuracy. The electromagnetic or EM spectrum covers a wide range of frequencies or wavelengths. The spectrum includes all communication frequencies such as satellites and broadcasting frequencies, but also include the frequency ranges of extraterrestrial sources studied by astronomy. These ranges include gamma ray and X-ray space telescopes, as well as some optical and radio telescopes. For Earth-bound observations, we are limited by the atmosphere. Atmospheric absorption limits the EM radiation that reaches the Earth's surface, with gamma rays, X-rays, and most ultraviolet light being blocked by the upper atmosphere, while radio waves, as well as visible and near-infrared light, can pass freely. This phenomenon is known as the Earth's atmospheric window, with the windows being those portions of the EM spectrum that allows transmission through the atmosphere, which is why Earth-based telescopes are typically optical and radio telescopes. The window for radio frequency can loosely be defined as the region between the far infrared astronomy and the boundary where the atmospheric opacity blocks out very long radio wavelengths. This radio band is fairly broad, spanning from approximately 10 MHz at the low frequency end of the EM spectrum to about 1 THz, or about 5 decades in wavelength, from about 30 meters to approximately 300 micrometers. The radio band is too wide to be covered effectively by a single telescope design, and the surface brightness and angular sizes of radio sources span an even wider range. It is simply not practical to build a single radio telescope that is even close to optimum for all the radio astronomies. So a combination of single telescopes and aperture synthesis interferometers are needed to detect and image radio astronomy sources. The simplest and also most sensitive aperture antenna is a waveguide horn, such as the horn antenna at Bell Labs. This small horn antenna was used by Phineas and Wilson to actually detect the 3 Kelvin cosmic microwave background radiation in 1965. By far the most common radio telescope today are parabolic dish antennas that provide large collecting areas and high angular resolution over a wide frequency range. These radio dish telescopes use their large reflector area to collect the signals, which is then focused onto a small feed antenna for recording. In general, the performance of a dish telescope will depend on the reflector area, the feed design, and the geometry between the reflector and the feed. The primary use of single dish antennas today are observing pulsars, which are time variable, so they are easy to separate from confusion by time-independent continuum sources. Also for spectroscopic observation of extended low brightness sources, again largely immune to confusion. They are there to complement interferometers by providing zero spacing data on extended sources, and quite often they are serving as elements for very long baseline arrays. Since larger diameters are needed to achieve these magical sub-arcsecond resolutions at radio wavelengths, the ideal radio telescope should have a large collecting area to detect faint sources. The largest fully steerable single dish today is the GBT, and it has a diameter of about 100 meters. But every practical single dish radio telescope has relatively low angular resolution and pointing accuracy, has a small field of view and limited sensitivity. gravitational sagging, telescope deformation caused by differential solar heating, and torques caused by wind gusts combine to limit the mechanical tracking and pointing accuracy of these large dishes, and the continuum sensitivity of a single dish is strongly limited by confusion at frequencies below 10 GHz. Aperture-synthesis interferometers, however, consist of an array of moderately small dishes, where the aperture of a single dish is determined by the dish diameter. The aperture of an interferometer is equivalent to a dish the size of the longest distance over all the antennas, called the longest baseline. Meerkat has a maximum baseline of approximately 8 kilometers, which enables it to measure radio sources with arc-second resolution at L-band. Having multiple dishes over a large area also help to mitigate other practical problems that plague the single-dish telescopes. Some examples are vulnerability to fluctuations in atmospheric emission and receiver gain, vulnerability to radio frequency interference, as well as a decreased vulnerability to point shifting because of atmospheric refraction. In fact, the geometric area of an interferometer of n dishes can be arbitrarily large, which is what is allowing a large international collaboration to build the SKA. To explore how single dish and interferometers work, we need to do a little math. Parabolic reflector antennas collect and focus planar waves from a distant source onto a single focal point, acting very much as a primary mirror for the radio telescope, providing an effective collecting area equal to the projected geometric area of the dish that can be used over a wide range of frequencies. This then raises the inevitable question: how far away must the point source be for the received wave to satisfy the assumption that they are nearly planar across the reflector? And the answer to this is the source must be further away than the far-field distance. And where this far-field distance is actually just defined for a dish of diameter d at wavelength lambda, given by a simple relationship twice the diameter squared divided by the wavelength of the source. If the distance to the source is far less than this far-field distance, we will find path length errors, which will introduce phase errors in the waves coming from the off-axis portions, which is the edges of the reflector. The consequence of this is that the effective collecting area is reduced and it degrades the antenna pattern. Observing sufficiently distant point sources ensures we can safely assume we are measuring planar waves, and we can fully describe the signal collected in terms of the antenna response pattern. Because we are basing our definition on the assumption of incidental plane waves from a distant point source, the antenna pattern is also sometimes referred to as the antenna's point source response. For simplicity, first let's assume we are measuring the antenna response of a uniformly illuminated one-dimensional aperture of width d at wavelength lambda. Please consider the first column of graphs here. This uniform illumination means that our receiver signal has a constant signal strength over the entire aperture, which we can easily represent using a block or step function with an amplitude of 1. But radio antennas do not measure the signal strength directly. Rather, they measure the antenna response, which is the Fourier transform of our step function. We know the Fourier transform of the step function is the sinc function, and thus the far-field pattern of an uniformly illuminated aperture is simply the sinc function, the second plot of the column. To obtain the antenna power spectrum, we have to square the antenna field pattern. This results in a dominant central peak in the power spectrum centered around 0, and this peak is called the main beam. The small ripples emanating away from the main beam is called side lobes. The width of the main beam sets the size of the smallest radio objects that can be observed. This is also called the telescope's resolution. But this is the main beam for a dish with aperture of 1, so a unity. To scale our result to the actual aperture size of our dish, we apply the Fourier transform's similarity theorem. This provides us with a relation of the beam width of an aperture antenna inversely proportional to the projected aperture size in wavelength, while the on-axis field strength is directly proportional to the projected aperture size in wavelength. Thus, through the similarity theorem, we have obtained a general scaling relation between the dish main beam size and the observational wavelength, with some constant that is proportionally dependent on the illumination taper. What that means is that we see for a large dish where the aperture is much larger than the wavelength, so d is much larger than lambda, the diffraction limited resolution of a uniformly illuminated aperture antenna is just under the ratio of the source wavelength divided by the dish diameter. So the ratio there is actually 0.89. So considering a slightly more practical feat, such as those used for parabolic antennas, these dish antennas cannot illuminate a large aperture uniformly. A better approximation for their illumination is a cosine tapered field pattern. So here, please consider the second column of graphs. Compared to the uniformly illuminated aperture, the taper increases the beam width to 1.2 times the aperture size in wavelength. In fact, this beam width is typical for most radio telescopes. So how do we relate this antenna main beam with observing astronomy sources? Radio astronomers use the angle between the half power points of the main beam on the power spectrum to specify the angular width of the main beam. We call it often the half power beam width or the full width between half maximum points. This half power beam width is sometimes called the resolving power of the telescope because two equal point sources separated by half power beam width are just resolved by the Rayleigh criterion. So we see the field pattern of a one-dimensional aperture is simply the one-dimensional Fourier transform of the aperture field illumination. So we can easily generalize to a more realistic case of a two-dimensional aperture, where the electric field pattern of a two-dimensional aperture is the two-dimensional Fourier transform of the aperture field illumination. The two-dimensional counterpart of a uniformly illuminated one-dimensional aperture is a uniformly illuminated rectangular aperture of side lengths dx and dy. Similar to the 1D case, we will convert the aperture length into units of wavelength by dividing the length in the aperture by the source wavelength lambda. This yields normalized UV coordinates, where u is equivalent to x over lambda and v is equivalent to y over lambda. So we have now defined the UV plane and it is perpendicular to the antenna aperture plane. When a point source is observed, the aperture, remember we call it the primary mirror of the radio telescope, is pointed towards the source, which means the direction from the origin of the UV plane to any distant point source can be specified using parameters L, the sine of theta x, which represent the angle between the vector pointing at the source and the yz plane, and m, the sine of theta y, the angle to the xz plane, thereby defining a two-dimensional Fourier transform of the aperture field illumination, where m is the y-axis analog and L is the x-axis analog. This Fourier relation is actually a fundamental concept in radio astronomy imaging. Most apertures associated with reflectors and lenses are circular though. And just like in the 1D Fourier calculation, the Fourier transform of a sinc function with a main beam and side lobes. But now the power pattern of the uniformly illuminated circular aperture is known as the array pattern, and the solid angle of a Gaussian beam is the half power beam width, scaled by pi over 4 times the natural log of 2. It is also worth noting that the perfectly sharp illumination edges of the aperture shown in our examples cannot be achieved in practice. In reality, Any illumination extended beyond the reflector aperture is called spillover. Most antenna receivers will see spillover radiation from the surrounding structure as well as the ground at lower elevation. Most swirls are excellent absorbers and emit blackbody radiation at the ambient temperature of 300 Kelvin. This additional ground radiation will contribute and significantly impact the system noise of the radio telescope at lower elevations. But the desired sub-arc second resolution of very large diameter radio telescopes can only be achieved by using the principle of interferometry to synthesize a large effective aperture using a number of smaller antennas. Let's start with a simple radio interferometer, a pair of two telescopes, two antennas, whose voltage outputs are correlated. Assume two identical dish antennas, separated by some distance. The vector between the dishes we will define as the baseline vector b, and the length will be equal to the line of sight distance between the two dishes, and in this case the direction of vector b will be pointing from antenna 1 to antenna 2. Both dishes will point in the same direction specified by the unit vector s, and theta will be the angle between the baseline vector b and the vector pointing towards the source s. Also, both antennas are recording data, and the output voltage V1 of antenna 1 is the same as the output voltage V2 of antenna 2. Now, although both dishes are pointing in the same direction, if we consider a plane wave from a distant point source located off-center and moving in the direction of the dishes, we see that the signal, the plane wave, will reach antenna 2 first and must travel some extra distance to reach antenna 1. So the arrival of the signal at the two antennas is out of sync, reaching antenna 1 at a slightly later time than antenna 2. This time lag is called the geometric delay and represents the additional light travel time to antenna 1 for a plane wavefront for a source at angle theta from the baseline vector. So although both antennas measure the same signal, the arrival of the signal at the two antennas is out of sync, which means the signal measured by antenna 1 lags behind in time by its geometric delay relative to antenna 2. So the output voltages of the antennas will now be correlated in the back-end correlator of the interferometer. The correlator output response is a complex signal whose amplitude R is proportional to the flux density of the point source and whose phase will depend on the delay and the frequency of the plane wave arriving at the dishes. As the Earth rotates, the position of this point source changes with respect to the antennas, and consequently the source direction relative to the baseline vector, the theta angle, will change over time. This means that the geometric delay between the two signals will change, and the correlator output voltage R will vary sinusoidally as the source moves. The correlator output over time is thus a quasi-sinusoidal interference pattern, which we typically call fringes. And the broad Gaussian envelope of the fringes shows the primary beam attenuation as the source moves through the beam of the dishes. The reason interferometers can determine the position of compact radio sources with unmatched accuracy is exactly because of these fringe patterns. The fringe phase makes an exquisitely sensitive measure of source position if the projected baseline is significantly longer than the wavelength of the source signal. Also, since the voltages V1 and V2 are proportional to the electric field produced by the source, the correlator output amplitude is proportional to the flux density of the point source, and thus the correlator response is a time average response, which means unwanted signals from very extended radio sources such as the cosmic microwave background and the atmosphere above the telescope will be measured as uncorrelated power noise and averaged to zero in the correlator response. So how do correlation and large interferometers achieve their accuracy? As we have seen, each antenna measures the Fourier transform of a point source response of the astronomical source. And from the convolution theorem, we know that the convolution of two functions is simply the product of their Fourier transforms, which means each two-element correlator, each baseline, measures one Fourier component at any given time. So to improve the instantaneous point source response pattern of an interferometer, we require more Fourier components, that is, more baselines, requiring more elaborate interferometers and therefore more antennas. An interferometer with more than two antennas, let's say n antennas, contains in the order of n squared pairs of antennas, each of which is an independent two-element interferometer. The point source response obtained by averaging the output of all the two-element interferometers is called the instantaneous synthesized beam. And we see this instantaneous synthesized beam rapidly approaching a Gaussian as more antennas are added. The synthesized main beam of a four-element interferometer shown in the slide is already nearly Gaussian, with the angular resolution given by the wavelength lambda over the maximum baseline. But the side lobes are still significant, and there are large negative bowls caused by the lack of spacing shorter than the diameter of the individual antennas. All of this can be improved by adding more antennas, but there are also some software imaging techniques that can be used, which is generally why we refer to the synthesized beam as the dirty beam. More Fourier components can also be added over time. As we have seen, the Earth's rotation varies the projected baseline coverage of an interferometer whose elements are fixed to the ground, resulting in the measured brightness distribution of a source simply being two-dimensional Fourier transforms of the measured visibilities in the UV plane. If we let U be the east-west component of the projected baseline in wavelengths, and V the north-south component of the projected baseline in wavelength, for observations over a 12-hour period centered on source transit, each two-element interferometer or baseline will trace out a complete ellipse on the UV plane. If the interferometer has more than two elements, the UV coverage will become a number of concentric ellipses. For sources near the celestial pole, the 2D synthesized beam is nearly circular, but the north-south beam width becomes larger for sources near the celestial equator. As the size of the baseline increases, interferometer arrays are no longer coplanar, and Earth rotation fill in a three-dimensional volume. For this situation, the UVW coordinate system is implemented to describe any baseline vector B in 3 dimensions. Again, U, V, and W are all components of the baseline vector in units of wavelength. As before, the U and V axes point east and north in the UV plane. But now the W axis will be normal to the UV plane, and the W axis generally points in the direction of the target radio source, here indicated by unit vector S. As before, the source position is specified in relation to the UVW coordinate system, and any arbitrary direction vector S can be specified in L, M, and N components, where L and M are still defined in terms of angles to the YZ and XZ planes, respectively. Now adding N to describe the direction angle between the W axis and the unit direction vector S, which will make L, M, and N projections of the direction vector S onto the UVW axes, with the L, M, and N components called direction cosines. The result of all this mathematical footwork is a three-dimensional generalization of the measured complex Fourier components, also called visibilities. It is important to note that this equation is no longer a three-dimensional Fourier transform. However, if the W component can somehow be made zero, the equation again becomes a two-dimensional Fourier transform, which can be inverted to give the source brightness distribution in terms of the measured visibilities. This can be achieved by imaging only a small field of view whose W components is very small, and applying this concept to wide field images imaging two-dimensional Fourier transforms by breaking them all up into smaller facets, much like fly's eye, inverting them and later merging the facets can make up the final wide image. Natural radio emission from cosmic microwave background, discrete astronomical sources, the Earth's atmosphere and the ground is simply random noise that is nearly indistinguishable from the noise generated by the receiver electronics. Yet, as we mentioned earlier, the correlator output amplitude is proportional to the flux density S of the source. And this is because the voltage contribution from broadband sources, such as the CMB and the atmosphere, are almost completely uncorrelated and average out over time. While the source's noise power is always greater than zero, and the noise from most astronomical sources are stationary, and therefore the main power measured from these sources are steady when averaged over timescales of minutes or hours. Thus, only the astronomical point source mainly contributes to the correlated noise. The sensitivity of an interferometer is determined by the faintest signal the telescope can detect. In other words, the point source RMS noise sigma s, and is mainly driven by the collecting area of the telescope alongside the observation bandwidth and the time spent observing the source. For a single dish, the geometric area is simply determined by the dish diameter, while the geometric area of an interferometer of n dishes is set by the combined area of all 10 dishes. Starting from our two-element interferometer, we see that by combining the independent correlator output of the two-element interferometer, we obtain a total point source sensitivity equivalent to the sensitivity of a single dish whose area equals the total area of the two-element interferometer, which is then improved by moving to an interferometer with n dishes containing nearly n squared independent two-element interferometers. For these large interferometers, the total effective area becomes equivalent to the combined area over the baselines, and the point source sensitivity sigma s can be calculated as shown. To summarize then, we see the angular resolution or ability of a radio telescope to distinguish fine detail in the sky depends on the wavelength of observation divided by the size of the instrument. Because radio telescopes operate at much longer wavelengths than do optical telescopes, radio telescopes need to be much larger than optical telescopes to achieve the same angular resolution. As a consequence, the history of radio astronomy had been one of solving engineering problems to construct larger telescopes and continually increase angular resolution, ultimately resulting in the high angular resolution of radio telescopes today being achieved by using the principles of interferometry to synthesize a very large effective aperture from a number of smaller antennas. This concept of interferometry can be described by considering a simple two-element radio interferometer, with the signals from an unresolved or point source alternatively arriving at the antennas in phase, constructive interference, and out of phase, destructive interference, as the Earth rotates, which cause a change in the difference in path from the radio source to the two separate elements in the interferometer. And this produces the interference fringes in a manner similar to what would happen in an optical interferometer. If the radio source has a finite angular size, then the difference in path length to the elements of the interferometer varies across the source, and the measured interference fringes from each interferometer pair thus depend on the detailed nature of the radio brightness distribution in the sky. Using cross-correlation of these measured signals, each two-element interferometer thus measured one Fourier component of the brightness distribution of the radio source. Movable antenna elements combine the rotation of the Earth, can sample a sufficient number of Fourier components with which to synthesize the effect of a very large aperture and thereby reconstruct high-resolution images of the radio sky. With the computationally expensive task of doing the continuous Fourier transforms to obtain the images from the interferometer data accomplished using high-speed computers and fast Fourier transform algorithms. For those interested in more full derivations of the equations and also more detailed discussions of the methods shown All of this can be found in the listed references. Also, for those who want to have a more practical feel of the UV plane, especially for the Meerkat telescope, Python Jupyter notebooks are available that can be run on any system through Google Colab. Thank you very much.